Get started. So today we have Iqbal from Durham University who will tell us about Goldstone modes and non-invertible symmetries. Go for it.
Okay. Hello everyone. So I want to begin by first thanking the organizers for inviting me to be here at this wonderful workshop. I've been having a really great time. I've really been enjoying the talk and talking with all of you. So let me tell you the title of my talk. My talk is called Non-invertible Symmetries and Goldstone Modes. And I'd like this to be quite pedagogical, so please interrupt me with questions if you have any. What I'm going to do is provide some background about non-invertible symmetries in the context of one particular system. I think everyone knows this system that I'm going to talk about. And so it's kind of interesting that there seem to be structures within that system that we were not, at least I was not aware of until last May. So I'll tell you about those structures, and then I'll tell you how to organize them in terms of non-invertible symmetries. And finally, I will derive a Goldstone theorem for these non-invertible symmetries. So that's the goal for the next 40 minutes or so. And this is mostly based on some work I did with Iñaki Garcia-Xavaria in November of last year. Okay, so I want to begin by giving some sort of a general background. Sorry, is this working? Yes, okay. I want to begin by giving some sort of very general background. So let me just remind you all, what is the Landau paradigm? The Landau paradigm is the idea that the way in which we organize the phases of matter, in other words, the things that can happen in the universe at long distances, the way in which we organize these in terms of patterns of broken and unbroken symmetries. A solid is a system that spontaneously breaks translational symmetry. A superfluid is a system that spontaneously breaks a U1 global symmetry, and so on. And so this Landau told us that we can use symmetries and their breaking and their not breaking to classify phases of matter. And furthermore, we can also understand critical points between phases in terms of universal theories that depend only on the patterns of broken and unbroken symmetry, and that they don't care about the microscopic detail. So these two ideas, in this room, everyone is very familiar with all of this. And this works spectacularly well for many phases of matter. You know, it's the cornerstone of our understanding of many body physics. Now, however, much modern work, the things that everyone in this room works on right now, they really involve phases and transitions between them that do not fit into this paradigm. Okay? So here are some examples. The first example is massless QED. That's a theory that everyone here knows, I think, and it'll be the focus of this talk. I'll tell you about some structures that exist in massless QED. There are many others. So, for example, topological order is something that many people in this room study. Many of the talks in this workshop so far have been about that. And topological order, almost by definition, does not fit into the standard Landau paradigm. Okay. And there are many other examples. There are just listed some things that I like here, but there are many other examples that everyone here knows about again. But the sort of philosophy of this talk, and really about this idea in general, is that I'd like to imagine that we're working towards building a new Landau paradigm by using new sorts of global symmetries, using non-invertible symmetries, using higher form symmetries. I'll remind you of all of those things. And I think it's quite possible that this new Landau paradigm that treats these new forms of symmetries on the same footing as the old ones will actually allow us to classify everything. Okay? This is my secret belief. We're not there yet, but I think it's quite reasonable to think that this will at some point happen. Okay? So today I'm going to sort of give you an example about how you can use non-invertible symmetries to recreate one of the features of the normal Landau paradigm, the instance of Goldstone modes. Okay, so before I go on, are there any questions about this sort of philosophical? Everyone happy with this philosophy? Okay, seems like you are. Okay, good. So can we do better? So now in this talk, I'm going to discuss new ways to think about a very familiar system. And this system is just massless QED. Let me remind you of the action of massless QED. I will always be in 4 dimensions. Okay. So this is the action. All right. There's a fermion field, and there's the Maxwell field strength tensor. It couples, the Maxwell field A. It couples to the fermion in the usual way, and there's a kinetic term for the Maxwell field. And physically, this is a bunch of massless fermions, and they interact via electric fields. All right. So this is what's going on. Each fermion creates an electric field lines. So now the question I want to ask everyone is, what are the symmetries of this system exactly? What are the exact symmetries of this? And again, I think I did not know the answer to this until last May. Right? So because this is actually kind of subtle, I want to begin by talking about a simpler system. Let me first freeze electromagnetism. Okay. In other words, I view A as an external gauge field coupled to the fermions. It's not dynamical, it's a frozen external field. Okay, so then I ignore this term, of course, and now the global symmetries are really very well understood, right? I have a vector current, which is psi bar gamma mu psi, and I can set things up so that this vector current is conserved, d mu j mu equals to 0. And I also have an axial current, psi bar gamma mu gamma 5 psi, and famously, this is not conserved, right? And one loop in the fermions, you do a little calculation, and you find that the divergence of the axial current is non-zero. Instead, this is given by F wedge F, where F, I remind you, is the field strength of the fixed external source. Okay. So in modern language, we call this a Toft anomaly. And the key point here is that the operator on the right-hand side of this is a fixed external source. Okay. So if you want, you can turn this equal to 0, and then the axial current looks like it is conserved. And in general, whenever you have a Toft anomaly, you actually have more predictive power than before. You can usually say more about your system than before. So this doesn't, though the language is that the symmetry is broken, it's really not broken in terms of predictive power. When you have a Toft anomaly, you can tell more than you could before, and the symmetry is really still there. Okay, in every useful sense of the word. Okay, are there any questions about this before I keep going? Everyone happy with this? So I'll use a Toft anomaly to refer to an anomaly where there's a right-hand side has a fixed external source, and I'll use ABJ anomaly to refer to the other situation. I'll discuss in the next slide. Okay. So now that we have this, let's turn on electromagnetism again and see what happens. Okay. So now that we understand this, let's now fluctuate the gauge. Okay. So to understand what happens now, we're going to have to generalize symmetry a little bit. I'm going to first review ordinary symmetries and then generalize them in a few different directions, and then I'll specialize again to normal massless QED. Okay. So let me just remind you about some words about ordinary currents. If you have, just think about your favorite system that has a U1 global symmetry, it'll have a conserved current, just conserved. And what does an ordinary current count? An ordinary current counts particles. Okay. And so here are some particle world lines, and you can count all these particle world lines by integrating over a codimension 1 manifold. Okay. In normal language, we call this a time slice, right? What you do is you integrate on one time slice. You integrate over all volume in that time slice, you count all your particles. And then the point is that charge is conserved. Okay, so you can do that thing at one time and do it at a later time, and you get the same answer. So a fancy way to talk about this is that this construction defines a topological codimension 1 surface operator. It's codimension 1 because it's a time slice, which is just only in the time direction. It's topological because you can move it up and down in time and you get the same answer. But it should be clear from these formulas that you don't need to move it just up and down in time in a rigid manner. You can sort of bulge it upwards, in one space here, just wiggle it like this, and you'll always get the same answer. In equations, that's because d star j is equal to 0. If you integrate star j, you can wiggle this around, and you always get the same answer. Okay. This is a very fancy way to talk about an ordinary conserved charge. An ordinary conserved charge is a codimension 1 surface operator. And also, finally, it's normal to take this and exponentiate it. We often take the charge operator Q and exponentiate it to get the actual object that generates a finite phase rotation, where here alpha is the phase that I'll be rotating by. So this is all very familiar stuff from textbook quantum field theory. The words topological operator for normal symmetries were not used in most textbooks, but they could have been. There's nothing new here. Okay. This is a normal global symmetry. This is nowadays called a zero form symmetry because, of course, because we can now think about ways to generalize it to sort of higher forms. So let's now come to a 2-index current. Okay, so this is what defines what's called a higher form global symmetry, which I first learned about from this very nice paper that's influenced, I think, many of us by Gaido, Kapust, and Seiberg and Willett. And a 2-index current doesn't count particles, it counts strings. Okay. And so that's what the extra index does. It tells you sort of which direction the string is pointing in. So the conservation equation looks like this, and in form language, it looks exactly the same. Now, a 2-index current counts strings. Note that if you're counting strings, you don't count them in the same way. So imagine there's a bunch of strings poking through the screen. if you want to count all of them, you don't need to integrate over the full room, you just integrate over the screen of each of the string pokes it, and then you can move your integral region, that's codimension 2 manifold, the 2 surface, you can move it upwards in space, sorry, you can move it forwards in space or upwards in time, and you'll get the same answer. Okay. So the point is, a higher form symmetry, the 2 index current, defines a codimension 2 surface operator, which is topological. Right? So this is now called a one-form symmetry. Through an unfortunate accident, the 1 here is off by 1 from the number of indices there. I hope it's a little bit easier if this had lined up exactly, but a one-form symmetry is what counts strings. Okay. So and often, again, we normally exponentiate this to get something that creates a finite phase rotation on these strings, create this operator. So this is the idea of a higher form symmetry. Are there any questions at this point before I keep going?
So I have a TU,
Yeah.
which is considered.
Which TU, the stress tensor? Yeah. So sorry, I should have stuck some anti-symmetry indices here. It's really important this is anti-symmetric. Okay. Yeah, you can see this equation makes no sense if it's not. It's really important it's anti-symmetric. If it's symmetric, well, TU does not count strength, it counts stress energy. Yeah. So good question. Yeah.
What is the space time dimension for your picture? Is it 3?
Oh, good. So this is a little bit, so I always put this picture here, but the truth is I think most people think about it slightly differently. So let me compare it to this. You see here on the screen world sheets, right? And here's the particle world lines, right? And here's my codimension, my codimension 1 integral, which you can see hits all of these things. That's why it's conserved, it's up in time. So here what's actually happening is, this is the string world sheet, okay? And this is the surface operator, this one right here. So it's 3, like you said.
Oh, okay.
But most people, when they see this, they think the other way around. And the truth is, I don't dwell on this because it doesn't really help anything. But real aficionados will notice that this is the 2-dimensional string world sheet, and you can hit it. Yeah.
Now I got a few of these surfaces.
Yeah, that would help. That would help. Yeah, that would help make clear, I think, the difference. But to be honest, yeah, I do this in PowerPoint, and it gets a little bit annoying to draw too many. Yeah, absolutely. Good. Any other questions? Okay. So, so this idea, it's very simple and has received a lot of attention in recent years because I think it's really the right way to think about many concepts where you have extended objects. And almost the point of gauge theory is that you have extended objects. So I think this is the right way to think about many things in gauge theory. Okay, so this is a one-form symmetry. Okay, so now let's return to our problem. Okay, remember, we're talking about the symmetries of massless QED. So now, I now make a dynamical gauge, right? Now what happens? So we used to have a vector current, but now the vector current has been gauged. It couples to this dynamical gauge field, and it's just no longer a global symmetry. That's the fact. The vector current is gauged. It's not a global symmetry anymore. And what this philosophically means is that it probably does not usefully constrain the dynamical content of your theory anymore. A gauge symmetry is important for a description of your system, but you want to try to extract dynamics in terms of global symmetries. But you do get a new ingredient now, right? You have this dynamical gauge field, and there's now a new one-form global symmetry, whose symmetry current is given by this. You take the field strength of your gauge field and hit it with an epsilon, and you get anti-symmetric object J mu nu, which is obviously conserved by the Bianchi identity. Okay. So physically, what this means is this thing counts magnetic field lines. Magnetic field lines are strings. In ENM and normal ENM with no magnetic monopoles, those strings are conserved. They cannot end in space or in time. And so there's a global symmetry associated with the conservation of those magnetic field lines. That is this one-form global symmetry. Okay. So this is interesting. You can have a surprising amount of fun with this. So for example, this one-form global symmetry, you should now ask, how is it realized? Is it broken? Is it spontaneously broken? Is it unbroken? And so on. And you can really think about the 4D photon in our universe, the one that you used to see me. You can really think about that as the Goldstone mode of spontaneous breaking of this symmetry. And so if you ever lay awake late at night, worrying why is the photon massless, I think this is one way to understand that the 4D photon is really massless because the Goldstone mode was spontaneously broken.
Yeah, actually, so suppose the photon also have no electric charge. Don't have to say there are two.
There are two of them.
Yeah, right?
That's right. Yeah.
But then but the number of photons is still the same.
Yeah.
I wonder, is there like a match between number of Goldstone modes and their?
Yeah, they have a mixed anomaly, the two symmetries. So you can, I think a fancy way to say it is that the electric and the magnetic one-form symmetries, they have a mixed anomaly. So you can saturate all of the broken word identities with just one dynamical degree of freedom. Yeah, and that's an awfully fancy way to say that they're basically this, they're intertwined in some way.
Is there a count kind of?
Yeah, so there is so people here worked on this a little bit. I think you can do accounting, but in most situations it's pretty, something, I'm not sure actually. I just said I'm not sure. There's been some interesting work like if you have a background magnetic field and the sort of zero form and one form symmetries become mixed up in some way, you get some interesting phenomena that Yuri worked on. So it can be intricate. I feel like there's been people here probably know what's better than me. I think Thomas Brown or maybe you guys also did some work on this. Is that correct? They're making accounting. Yeah, that's right.
So usually, for their form symmetry, commutators they combine charge, right? Both charge. But this is generated to the surface charge or something.
Yeah.
And the cross section that might be something different from the ordinary charges, and it becomes like interesting thing which happens not in zero form symmetry, but
So I think the short answer is yes, and it's fun. I think is the answer. Yes.
So does anything change for massive fermions?
For massive fermion. Oh, good.
Yeah.
So the truth is, this slide is actually works for anything. Right? Yeah. The next thing will be different for massive and massive. So I'm getting to that. At the moment, it doesn't matter.
Again, when you say it's Goldstone mode, so you can of course have photons of arbitrary that. So are you thinking in terms of soft photons, or this is?
Yeah, I'm really saying that as p goes to zero, it's the fact that there's no gap, and that gaplessness I think can be thought of in this way. That had to be the case, basically.
Yeah.
At high p, of course, always lost.
Yeah, because I mean, you think about again scattering or as a matrix. Picture.
Yes.
Yes, very relevant.
Yes, no, absolutely. Yeah. So I think that the thing, one way to think about this is that you can imagine the Maxwell action as being a Goldstone mode action. You see, it has some terms in it, and just like the pion Lagrangian organizes things from vector field theory in some way, you can think about the Maxwell action as doing the same thing. I think I'm not sure that you really get much more predictive power in this because we understand Maxwell action so well already. So it's a new way to think about, its philosophical role in life. Yeah. So I'll just say that the truth is, all of us, like when I teach quantum field theory, I lie a little bit, right? When I teach gauge theory, I say, okay, the photon is massive, it's a gauge field. But this is just a lie, I mean, that's not why it's massless. That's why you don't write down a bare mass term for the photon, but it's not why it's massless. You can have a Higgs phase and it's very massive in that phase. So, you want more information. And I think this is a good way to organize that information.
Did I get it right? If you have the restored phase, you have a superconductor?
Yeah, that's right. Yes, that's right. Indeed. The unbroken phase of this symmetry is the superconductor. Because it's unbroken, there's no longer a need for a massless field, and indeed there is not a massless field, right, in the superconductor. And you can think about the order parameter and so on. All of this makes sense.
So there's also this discussion, the Goldstone modes in this language of asymptotic symmetries.
Yes.
Yeah,
That's right.
That's right.
So
there, I mean, the picture is you have this. Large transformation across.
That's right.
Certainly.
So there's some overlap for sure, but it's a little unclear to me exactly what the connection is, because in a sense that I believe that their ideas are almost independent of the phase. You see, there's clearly some connection because there's the vacuum, their vacuum is non-degenerate, and this is non-degenerate, and there's something, but we've not been able to make the connection as precise as I thought it would be.
Yeah, I think that would be very interesting. So because there, it's this. It's Goldstone symmetry of the two spheres, right? And the difference between the different vacuolar numbers of massless photons.
Absolutely, yeah. So there really should be some connection. I completely agree, but we've not been able to make this very precise. I'm not aware of anyone making this very sharp connection. Excellent. Okay. So so basically this is just to sort of show you that they're really this higher form symmetry is present in the most familiar field theory that all of us know. Okay. Now,
if there is a magnetic monopole, photon would be massive or what?
No, very, very good. So the kinematics is a little bit different in that higher form symmetries are very happy to emerge. Okay. So if you have a massive magnetic monopole at scales below the magnetic monopole mass, then this symmetry emerges again, and you still get a massless mode. Okay, this is different from zero form symmetry. For zero form symmetry, it's pretty much the case when you have a Goldstone mode. If you break the symmetry in the UV, then the Goldstone mode immediately picks up a mass. That's actually not the case for higher form symmetries. Yeah. And there's various ways to understand this, but yeah, this is a qualitative difference actually. Yeah, it's an excellent and somewhat confusing point, I think. Yeah, it's an excellent point. Good. Okay.
You have a plasma.
Yeah.
Here.
Yeah.
Your photon would acquire mass.
Yeah, so this is extremely fun. I don't want to do it. I'm going to give you a little bit and then no, but it's extremely fun because you see, if you think about this, you realize that say you want to describe a plasma, this is the right way to do it, right? Because to describe a plasma, you identify the global symmetries and you throw them into the hydrodynamic crank, and then the hydro theory pops out. And so we did this for MHD, and the hydro theory that emerges is a lot like the one that's in textbooks, but it's more general. Because it's not constrained by various textbook assumptions, but weak electromagnetic coupling and so on. So I think this is a useful and productive thing to do. It's also very fun to think about what happens to all of the symmetries in the plasma. So you can think about Debye screening in this way. It's a very fancy way to talk about it, but Debye screening is because a certain component of the symmetry is explicitly broken and a certain component is spontaneously broken, and there's various things that you can do with this. So this is lots of fun. I'd love to talk about it with you afterwards, but all the stuff you know and love with plasma physics can be reinterpreted in this language, and it might even be a useful way to reinterpret. Okay, excellent. So I'm going to keep going. Thank you for all the questions. I'm going to keep going to the main. This is great. But I'm going to keep going to the main thing, which I've not gotten to yet. So this is, by the way, we've only talked about this part so far. Okay, we have the fermions. That was the fun thing. So now let's now come to the fermions. Okay. So what's happening to the axial current? Right. Now remember, this looks like a symmetry of the Lagrangian, but it's not at the quantum level. At the quantum level, the divergence of J is F wedge F. And now, this F wedge F is not a fixed external source anymore. The photon is fluctuating, so this is a dynamical operator. Okay? And so, you know, it might just seem like this current is just now not conserved, right? The divergence of J is just not zero. It's equal to a non-trivial operator. All right? So I think you might just say it's just not conserved due to the ABJ anomaly. I'm going to call this the ABJ anomaly. Due to the ABJ anomaly, you just lose the axial current. And that I think is a reasonable viewpoint, and it's how I thought about this for a while. But it doesn't feel right. Okay? So let me tell you a few reasons why it might not feel right. You know, this isn't just some random operator. It's a very special operator in some sense, right? You integrate it over a 4-manifold, you get an integer. It feels special. But another way to say it is, remember the one-form symmetry had a two-form conserved current? Notice that you can write the divergence of the axial current in terms of this two-form conserved current in a way that makes this equation look sort of universal, right? This relates a universal object to something that looks universal. That suggests there's some interesting structure linking the two symmetries in some way. Okay? And so it turns out that this thinking that something funny is happening is true. The true situation is more subtle. It turns out this symmetry is not lost, but it's changed in some way. So I'm now going to tell you how it's changed, and I'm going to use that new way of understanding to derive I'll derive known dynamical principles from a new point of view. Okay. Is everyone happy with this? Good. So now, so here's a summary of the symmetry of the massless QED. Okay. We have a one-form symmetry magnetic flux conservation, and we have a non-conservation of the axial charge, which is given in terms of this two-form current that was appearing here. All right. And then we just sort of tell you in words what this thing means. What this equation here, right here, means is that if you have an axial charge and you have some dynamical magnetic field lines floating around, you are allowed to violate the axial charge, provided you simultaneously tie a knot in your magnetic field lines. Okay? That's another way to think about this formula right here. And you know, this feels really special, right? It feels like there's something interesting going on. And so the right way to think about this picture was explained recently in terms of non-invertible symmetry in these two papers. Okay.
Yeah. So I mean, could you think about it in the following way? That is, you introduce your axial vector field, so that introduces an imaginary part to your action, and then you take functional derivative of that, and that gives you your output. So that's big stuff.
Yeah. So indeed, you can always, of course, you can derive this equation from that sort of thing. That's a completely fine way to do that, but I think we're just reformulating the, It's just deriving it in a nice way.
Right, so how would you interpret, I mean, is there a way to think about this, this knot in that language?
From that language?
Yeah.
I think that,
So.
yeah, it's not so much the source for the axial charge that's creating this knot. The way to think about, let me come back to, I'll explain the knot in a little bit. I've not really told you, if you don't already know this knot story, you won't really learn it from this slide. So I'll explain the knot in a little bit. Good. Okay. So the right way to think about it is explained in two very nice papers from last year. I recommend this paper to everyone. I'm now going to give you a brief summary of the content of those papers. So because the current is not conserved anymore, there's no longer a conserved current. Okay, but you might try to make a conserved charge. So let me tell you how you would do that. So let's consider the following object. Consider star of the axial charge minus a wedge dA. Okay. Now, the divergence of this quantity that appears here is 0. Okay, because of the formula I put over there. So this is the divergence of this quantity, and now the current, you can't really think of this as a current though. Even though it's divergence, there's an A floating around in here, and therefore this object is not gauge invariant. Okay? So you should not think of the local density of this as being a useful thing. It doesn't make sense, it's not gauge invariant. But you might be like, okay, let's not worry about that. Let's just integrate this over a time slice or over some generic 3 manifold. If you do this integral, okay, then you get something which now looks a little bit like it's gauge invariant. Okay, the Chern-Simons form that appears here is actually gauge invariant under small gauge transformations. All right, but this object still has some issues. Let me tell you what those issues are. So what you normally try to do is you take this charge operator and then you exponentiate it in the following way. And this alpha is the angle by which you're doing your phase rotations. Okay, it's the angle by which you rotate the fermion fields. Now, this is e to the I alpha. It contains a bit which is a Chern-Simons term times alpha. All right. But that, as was pointed out to us in various talks during this workshop, that is not generically gauge invariant. Okay. This A wedge dA is not invariant under large gauge transformations unless the thing multiplying it is integer quantized. In other words, this alpha is integer quantized. But that's not good because alpha was the angle by which I was rotating. Okay. So when alpha is integer quantized, that makes this operator basically empty. Okay. Yeah.
Is it clear that this charge is an integer?
I'm going to always work with this charge being an integer. You mean, are you worried about integer versus half integer, or do you mean? Oh, okay. So I'm going to work in systems where it's compact and this is a minimum integer quantized charge. I think that's true for most normal systems. By this you mean this guy or the whole thing? The whole thing. The whole thing. I think, so they think about this actually, because at least changes in it are, right?
Yeah.
And so I think that means that it is for all intents and purposes. Yeah. Good. Okay.
To draw the second term, it's the axial charge, isn't it?
Yeah, the axial charge.
It's a number.
Yeah. This one alone, I think, is clearly an integer. And I believe your question was more about this thing, and I think that changes in it are, and so I think it should be. Yeah.
Yeah, I mean, like the talk yesterday.
Yeah.
Mentioned, right? I mean, this Chern-Simons term integral over S3, for example, is only
Yeah.
integer if A equals with CP4. Which
Yeah,
is
yeah.
A equals with the CP1 kind of.
That's right. That's right. Yeah.
Otherwise, it's not generally.
Yeah, that's a good point. Yeah. So I think the truth is, I don't think of what I always think about in this is sort of the fermion charge Hilbert space and then connecting things with that. So I cannot think of states. Yeah. Yeah, I think all I'm comfortable saying is that changes in this charge are integer. I cannot think of a dynamic process that will change the charge by a non-integer amount.
Yeah.
Yeah.
If
So
change by integer is okay.
That's okay,
good enough
that's good enough for all intents and purposes. It suggests that the Hilbert space might have some funny sectors that the charge is not an integer, and then you can think about that, but all the dynamics on top of that would be integer. So I think that's okay. A good question. Yeah, I'm not thought about it very carefully. Yeah.
So, I mean, for QED, is that also something you would get from the index theorem?
The index theorem is related to many things here. Yeah. So I mean, the index theorem is lurking in the structure of this, like all these things. That's right. Yeah. Absolutely. So it's another way to think about, like, you can use it to justify why the formula I wrote down is an exact formula, which is important for us. Good. Okay, excellent. So yeah, wow, I'm going a lot more slow than this. Okay, I'm going to speed up a little bit. How much time? Yeah.
You're getting an infinite number of questions.
Yeah, which is great, yeah.
Which is good.
Yeah.
So we're technically, theory, but let's
not invertible.
Yeah, I'm not there yet. I'm not expecting. No, yeah, don't worry. Yeah.
Just feel free to keep going. So let's all shut up.
Okay. Yeah, I was
Just keep going for at least 10 minutes.
Okay, good.
Okay, so we're not Q&A? Oh, no. I'm wrong. Never mind. You still have 10 minutes of the official talk time.
You'll talk. Okay, good.
Yeah.
Okay, so so I'll try to. What I'm going to try to do is try to make the official talk end at the time when the Q&A would have ended. Is that okay? Is that a reasonable?
I think that's fine.
Okay, we'll try to the official talk end at 10:20 this week. Then in that case, I'm right on track. Okay, good. So the point here is, you see, it feels like there's no useful conserved charge here. Okay, that's what's happened. Is I need to quantize this thing. Now, that's bad, okay? Because it means that we don't have a conserved charge. I mean, this is how I thought about this problem for a long time. I thought there is no useful conserved charge. But let us try anyway to make one, okay? So let me try to make a fractional rotation angle. Okay, let me try to do this. So in other words, I'm trying to rotate not by the good amount, by the good amount divided by n, where n is an integer. Okay? So I want to make sense now of this object. 2 pi over n star j minus a by dn. Okay. This is not invariant in the large rotation. But here's the idea of those two papers. This has a fractional thing in it, but that's okay. Let's introduce a new dynamical field, little a. Okay? Not in the bulk, because that would change the theory. But because I'm doing this integral over some time slice, I'm going to introduce this new dynamical field, little a, only on the time slice. Okay? So only on this codimension 1 manifold. Now I can write down the following quantity. Okay. It's 2 pi over n times the axial charge. Now, this is a new kinetic term for my new gauge field, little a. All right. It has the n in the numerator, so this is a completely well-defined object. And then I couple this little a to my photon field through this wedge product. Now, what is happening here? If you now take little a and integrate it out, let's just do that in a brutal way. Integrate it out. Okay, here's one quadratic that can do that. Then I get an equation of motion that relates little a to capital A divided by n. The n is in the denominator. If you plug that back in here, then it ends up being this thing over here. All right. So upon integrating out little a, I get this fractional charge. But this way of writing it makes everything completely gauge invariant. So in other words, this is the right way to write down the idea that you had over here. This is the gauge invariant way to do it. But it comes at a cost. You have to add a new degree of freedom on the defect. And that new degree of freedom is little a. So what have we done? We have constructed an object which is a topological charge operator. Okay? In other words, it counts a conserved charge, but now we have a new field, little a, living on it. Okay. So let me now say a few remarks about what this gives us. Okay? So first of all, here's my object, all right? This generates an arbitrary fraction of a root of unity where n is an arbitrarily large integer. It rotates all the fermion fields in this way. All right. You might at this point be sort of worried, why is it, just 1 over n? This is not important. You can imagine doing it many times to get like basically any rational fraction. Or you could directly write down a rational number by using a slightly fancier TQFT. What I did was I added a fancy topological quantum field theory on this defect. There are fancier ones that will rotate this by any rational angle. And so 1 over n here is not important. The rationalness at this point is still important. Yeah.
Is there a different a for every n? Or
it depends. You mean if you want to do it over and over again?
Yeah.
If you do this multiple times, you need a different a for every n. A better way to do it is really described in these papers. If you want to rotate it by a rational angle, you use not a different a for every one of them, but just a fancier TQFT that, morally speaking, has only one a in it. Yeah. It's just not this TQFT.
Yeah. So that's my question. So I mean, so sometimes you're saying, okay, you've taken care of this problem of large gauge translation.
Yeah.
And so it's something you can think of this as some constraint that embeds that in your vector actions that you're thinking about.
I wouldn't say it's a constraint. What I've done is, you see, remember I told you this picture about how the charge is conserved modulo this time and knots. You see, these new things I've added sort of account for the time of knots in a nice way. I think that's how I think about this. This little a is a new little guy I put on my charge manifold. The little guy runs around and counts the time with knots and does that in a good way. I think that's how I think about this new thing. It's not really a constraint on any of the dynamical fields. Yeah.
Right, but the whole thing is now just invariant under.
Yes,
you
yeah.
know,
So that's good.
Edge,
Yeah, yeah.
transmission.
Indeed.
is relevant.
Absolutely. But we didn't do that by constraining the dynamic
Yeah,
field.
I understand.
Yeah, okay.
That's, yeah.
Okay.
Wrong word here.
Yeah. Okay. So now this is called a non-invertible symmetry. It's an example of non-invertible symmetry. There's been a huge amount of work in this. We got instructions to that in Yuya's talk yesterday, actually. When I first started writing this talk, I started to put some names here, and then I stopped because it started to fill up this slide. So I'm not giving you references for it, but there's been a huge amount of work about other non-invertible symmetries recently. I want to just point out why it's non-invertible. Imagine acting with this guy and then acting with the opposite guy. So I act with plus n 1 over n minus 1 over n. Okay. Now, if I didn't have all this other stuff,
Changing the sign of n up there.
yeah, that's right. That's right. Exactly. Yeah, acting with one of them with plus 1 over n, then right below one with minus 1 over n.
So they're different fields.
Yeah, exactly. You need to put a new. You have to put a new little a on each of these two fields. Okay, a1 and a2. Yeah, exactly. Now you see, if these terms didn't exist, then of course this would all cancel out. You just get 1. Okay, so plus 1 minus 1, you get 0. Now this is not the case here, because if you try to fuse these two things together, this guy will go away. Sure, the sign is going to cancel, but the new dynamical fields that you added, those still live, right? And they will do things. When you combine these two things, you have like the diagonal combination of these two gauge fields floating around and doing something interesting. And so basically, once you act with it, you cannot unact with it. It is not invertible. Okay? Because you added degrees of freedom. That's basically one. Yeah.
Why do you have to implement inversion like this? You could simply replace I instead of 1, you take n minus 1. And that's like the inverse element. Huh?
No, you can never, because each time you act, you have to add some new degrees of freedom.
No, I'm not changing n at all. I'm not changing fields little a. I'm changing that little I. Oh, that's not an integer.
No, this I, that's I, the complex unit.
So you are not including any sort of 2 pi k over n. It's just 2 pi over n and that's it.
Yeah, that's right. At the moment,
okay.
yeah. But that's not important. Like I said, you can make a rational rotation angle, which is 2 pi k over n for k and an integer. You can do that as well. Okay.
But then exactly, it seems like there is a possibility of having two rational phases. 2 pi over n and 2 pi n minus 1 over n.
Yeah, what happens is those guys will each of them will have their own little gauge fields living on the defect. Those little guys will still exist, you see. You can cancel this stuff, but each of them having a new little gauge field, that will always run around the same for you.
Yeah. As a very minor comment, the action on psi that's written there will be invertible.
Yeah.
But the thing is, these things do more than just that.
Exactly. I'll give rest of it. That's right. I'll give an explicit example later where it annihilates something, and then it'll be clear that you can't invert it. Okay, good. So now you see, this is the right. I think this is the right way to think about the axial symmetry in QED. Okay. Now you see, this does stuff for you. You can derive constraints on things, on selection rules, and so on. You can do stuff with this. And what I want to do in the 15 minutes that I have left is prove a Goldstone's theorem for these new symmetries. Okay. It's not immediately obvious how to do this because it's not completely clear how to use this to do Goldstone's theorems. That's what I'm going to now tell you. Okay. So here we go. Now, what I'm going to do is I'm going to actually construct. Yeah.
Does it work for non-affiliated?
No, it doesn't. It has to be. It does. It has to be U1. Yeah. You see, it has to be U1.
I guess Mutual Salmon.
Yeah. That maybe you could make some sense of it, but the point is that it somehow has to do with the dynamics of the one form symmetry, the continuous one form symmetry. That's an important thing in making this whole thing work, and you don't have that for non-Everything gauge field. At best, you have a Zn. Okay, yeah.
So just a quick clarification question on the previous slide. That picture, just to be clear, what you're doing is you have two manifolds M3, M3 and M3 prime, which are slightly displaced, and you're deforming them, which you can because everything is topological.
Yeah.
And the question is, what happens when you bring them exactly on top of each other?
Exactly. Yeah. Exactly. Yeah.
And if it weren't for the fact that these are non-invertible, then that would just be trivial.
Yep. Absolutely. Okay. For normal charges, they just cancel. Here they do not. That's exactly the right way to think about it. Good. So now everyone knows what a non-invertible symmetry is. This is one example of non-invertible symmetry. We had other exampple yesterday. To point out, there's a lot of similarity between this and Yuya's talk yesterday. It's really very, very similar. Okay. So now I'm going to do this now in a slightly different way. Okay. So what I just told you was the earlier work. I'm now going to tell you a different way to implement this. And this is work that was done by me and Iñaki Garcia-Xavarria in Durham, and simultaneously by Avner Karsik in Cambridge. So there's another way to make a gauge invariant object here. Okay. Once you're allowed to put stuff on your defect, there's another way to do this, which is instead of adding a Chern-Simons term, let me just take this thing and introduce a new scalar field theta on the defect. So theta is a compact scalar field living on the defect. And now I'm making a gauge invariant in this way. If you think about theta as being a Higgs field, which lets me write A, or rather Stuckelberg field, I guess, which lets me write A minus d theta instead of just A. And from the point of view of divergences, this object is still topological. A way to see that is imagine extending theta a little bit off of the defect, and then take the divergence of this quantity. It's still 0 because this guy doesn't do anything to that divergence equation. But now you see this is a little bit different. It's a little bit simpler because once you have this new theta field on the defect, now you can generate this new thing. Now it is still topological and it's still non-invertible, but there's a few differences with the previous construction. All right. So let me call everything that appears here, this combination of things, J tilde. Okay. So notice that this guy is now the integral of a local density J tilde, okay, on the defect. That's an important point. It's going to be the point one follows. The other one wasn't. Okay, the other thing was not a local gauge invariant density. All this Chern-Simons stuff. This is the local gauge invariant density on the defect. Relatedly, the rotation angle here now can be completely arbitrary. I sort of mumbled to you before that previously had to be a rational number. You can get into endless confusion about whether a rational number is are the rationals continuous or not? It's like a quasi-philosophical point. But this alpha is just a continuous, angle. There's no sort of that. So in other words, the symmetry transformations are now relabeled by arbitrary U1 phase. And the point of doing this is that this version will actually let us prove an analog of Goldstone's theorem for these non-invertible symmetries. Right? So now I'm going to prove to you the Goldstone theorem. But before doing that, I want to prove to you the ordinary Goldstone theorem, but in path integral language. Right? So the argument I'm going to give you is something that me and Diego Hoffman came up with to try to prove Goldstone theorem for higher form symmetries. I think it's really the fastest route to Goldstone's theorem.
Can you?
Yeah.
I missed this. Can you repeat how you ensure gauge invariance by using
this thing?
Yeah.
So you need to take theta to transform like a Higgs field like a Higgs phase under gauge transformations.
I see.
And then this is gauge invariant.
Okay.
That's all. So I'm just introducing it to soak up the gauge invariant.
Okay.
That's theta's role in life. Good. So now let me just quickly prove to you the normal Goldstone theorem, and then I'll generalize. Okay. So I want to prove Goldstone theorem in Euclidean path integral language because everything I'm doing is in Euclidean. So this is not one of this. Think about normal symmetries. Okay? This slide is normal U1 global symmetries, right? So if you have a U1 global symmetry, then I have a conserved current, and there's a Ward identity for that conserved current, right? It says if you construct the divergence of your current in the presence of a charged operator with charge Q, it's not quite conserved. It's conserved only up to a contact term where these two locations coincide. Okay. This is the Ward identity for the conserved current. This is the definition of a charged operator in some sense. Now, let's take this equation and integrate it over the interior of a tree sphere. Okay. So divergence is really begging to be integrated over something. So I'm going to integrate it over the interior of a tree sphere at the center of which is this operator O of 0. Now what happens? This is the right-hand side first. I integrate the right-hand side. I'm integrating over this. I just get O of 0, this delta function. Let's do the left-hand side now. It's the divergence of J. I integrate it over the interior of the sphere that becomes the integral of J pointing outwards along the tree sphere. In other words, what I find is that the integral of J on the outside of this tree sphere, okay, is equal to just this object O in the middle. Okay? Now this equation is always true, it's an operator statement. But now let's take the VEV of this. Okay? You take the VEV, there's two things that can happen. First of all, the VEV of the right-hand side can be 0. In that case, the symmetry is unbroken because the charged operator VEV vanishes. And then I can't say anything useful, and then I'm done. Let's imagine the case though where the VEV does not vanish. In that case, the symmetry is spontaneously broken. But notice that the left-hand side has an integral on the outside of a 3-sphere of radius r, but the right-hand side does not care about the radius r. In other words, I can make this integral bigger and bigger and bigger, and this answer has to stay the same. And it's again the integral of a local object integrated over all the points in the 3-sphere, which means that this integral must go like 1 over r cubed, so that the integral of the volume of the 3-sphere cancels. This 1 over r cubed divergence is the Goldstone theorem. Okay, the Goldstone model. So this is a very fast proof of Goldstone's theorem in Euclidean path integral language. I like it because it makes it, I think, no hard. Everything I did is basically how you prove, the electric field was like 1 over r squared, elementary E and M. This phrases the Goldstone theorem in exactly the same language. Okay, same calculation. Yeah.
I don't like. Well, okay. I mean, so introducing the theta is really like introducing another matter field for the capital A gauge field.
Yeah, on the defects. Yeah, that's right.
No, I mean only on the defect.
It's only on the defect. It's only on this is important. It's only on the defect. Yeah.
So is there anything in the bulk?
No.
You can write down which actually, automatically make this defect have this.
Oh, I mean, you could imagine that you have a Higgs theory in the bulk as well, because you could use that. That's a specific case, but I don't want to think about that case.
Yeah. Okay.
Yeah.
So my real question is about suppose I do that, right? Suppose I have like a psi, the fermion, and capital A, and another Higgs field.
Yeah.
Then combining the psi and the Higgs field together, already give me a global U symmetry. Dagger.
Yeah, I think it's the truth is I think it'll only do that if you stay away from any vortex core, right? And in a sense, it's not. Maybe we can talk about this afterwards, but I think that you can formally write that down. But the idea is break down whenever there's a vortex, right? Because then d squared theta is not 0 at the vortex. And in the Higgs phase, that's the only time you have magnetic field anyway. So I think that you're sort of losing the interesting thing, I think.
No,
so, but,
just trying to whether that U1 is the same as your U1.
It probably is away from the magnetic field sector. I think it is obviously away from the magnetic field sector. When the magnetic field sector is there, then the other U1 is not conserved anymore. Okay, but this one still is. I think that's how it's going to go. But we can talk about this in more detail if you like. But I want to stress that I don't want to make any assumptions about the bulk field content at all. Because I don't want to assume there's a Higgs phase I can use. Okay, that's why I'm putting it only on the defect. Okay. So in the next 5 minutes, though, let me just quickly prove to you the Goldstone theorem that I wanted to prove. Okay. This is just normal Goldstone theorem. Okay. But by now, it should be sort of clear to everyone how this is going to work for the other Goldstone theorem. Okay. The one I want to prove. We can use basically all the same language. Okay. So what you do is you take your charged object, your charged operator, and put it in the middle, and you wrap it with this non-invertible defect, okay, on an S3. Right? The non-invertible defect is labeled by a rotation angle alpha. You take a derivative with respect to alpha. I can do that because alpha is really a continuous parameter. It's not rational. You don't need to worry about the philosophy. You can differentiate it. And then what happens is that it just brings down whatever was present in the exponent of the action, which was this thing I call J twiddle. Right? This is a well-defined local density. It's only defined on the defect, but for the purposes of this calculation, that's totally fine. So what I get is I get the integral of this density on the defects, okay, integrated everywhere over here. Okay. And then the correlation of that with this local operator in the middle must be exactly this. Okay. And from this step onwards, everything is exactly the same. All right. What you find is that this local operator must have a non-trivial correlation with the operator O in the middle. Should be a bit careful and show it's actually the connected correlator, which must be non-zero, which is what you want. And once you have a connected correlator between something on a defect and something in the middle, which is non-zero, the distance here again goes like R, you must have a gapless mode in the bulk to mediate that correlation. And that gapless mode gives you this 1 over R. What I've just done is I've proven to you that non-invertible symmetries have, this non-invertible symmetry has the Goldstone theorem in a very, very similar way. Okay? It should be clear that we needed the local density to make this work, otherwise it would not have this. Okay. So, so that's really the main point of this. I have something to say, but what I'm going to skip quickly through them and then I'll just stick around and I can tell you to people afterwards. Okay. So this is just one example of how you can get dynamical consequences from non-invertible symmetries. This is just as useful as a normal symmetry in this particular case. You might ask, what is the lower theory of this Goldstone mode? And this is the theory of an axion. Okay, so here's the theory that's the lower theory of the Goldstone mode. 5 years the Goldstone mode. Okay, So this is a normal Goldstone mode action. There must be a coupling phi f wedge f to create the non-invertible structure. This is necessary. Things to work out. And you might ask, why is the phi in the Axion theory, the U1 Axion theory, why is that field massless? All right. This is non-abelian gauge theory. This would not be massless. All right. So what you normally do is you say something like, oh, here's the theory, and then there's no U1 instantons. And that means that this coupling, even though it's not a derivative coupling, it doesn't give it a mass. Okay, these are the words that you normally say. And these words are all correct, but there's another way to think about this. It's massless because it is the Goldstone mode of a spontaneously broken non-invertible symmetry. That's another way to think about why it's massless. Okay. And this argument, the words that I just said here, they apply to other systems as well. Particularly, they apply to QCD in the massless limit. Okay, the pi 0 has a coupling that's just like this. And if you are into string theory, which maybe not, but if you were, this also protects the masslessness of many of the like fields in string theory. It turns out a lot of those fields generate non-invertible symmetries, and you can think about this plethora of R form fields and so on as being Goldstone modes of spontaneously broken non-invertible symmetries. I'm happy to explain that if people are interested. Okay, so let me skip through the next thing. This is fun, but I just don't have time to do this. And I just want to conclude with some quasi-philosophical remarks. You see, the truth is, I think the physical applications of these higher form and non-invertible symmetries are really still in their infancy. I think basic questions are still open. It's remarkable that we find that these symmetries lurk in really well-known systems. Okay, I think that's very exciting. And this basic question like which systems have these symmetries? Okay, Yuya told us about an example yesterday. I think they exist in many systems that we already know and love. It's not obvious to me when the symmetries have a Goldstone theorem in general. My construction was kind of specific to this one. You have to think about the details of each of them to figure out when there would be a Goldstone theorem, when there wouldn't be. And in general, I think that the phase structure of these things, what are the phase transitions, what are the critical phenomena, what are the critical points, all the stuff we do with the normal Landau paradigm, we should now redo in this new language. What I told you today was really the very basic first step in that, establishing a Goldstone theorem. And you can do fun stuff on a temperature. I'll tell you, if you're interested, I can tell you afterwards. You should think the right way to think about the theory called chiral MHD is to think about this non-invertible symmetry and put it at a finite temperature. I have been trying to build chiral MHD in this way with my collaborators. And finally, just in general, the new Landau paradigm built around these symmetries, I think is something that we should all try and explore and see what it gets us. Okay, thank you very much.
We might have time for like one really urgent question before coffee. Okay, so Gates, since you haven't asked any questions. Sorry,
Yeah.
sorry, Roger.
So you kind of told us that to introduce this non-invertible symmetries, you need to put some extra degrees of freedom.
Yeah.
in defect.
Yeah.
And then you did it with this theta, right?
Yeah, that's right. Yeah.
So, so this Goldstone theorem,
Yeah.
does it say anything about your original problem, which was massless?
Yeah. That's right. That's right. Yeah. So it does. Yeah, because you see, the degree of freedom is only on the defect, right? So that degree of freedom cannot create the power law correlation that I told you about. The power law correlation was always there. Okay. Because if you have a defect, it cannot have a power law correlation with something far away from the defect unless the bulk had a massless volume. So I created an object to show that to you. But this is now after you have this, you can now forget about what I did and just say there must be a massless.
Yes. So what is this in the original language?
Oh, it's there in the theory where the symmetry is spontaneously broken. It's the axion. Yeah, it's only there in some phase. It's not there in the free fermion phase. It's there in the phase where the symmetry is spontaneously broken, and then we would call it the axion. Okay. That makes sense.
Yes. But which program yet? So originally you just wrote mass. So
yes. Plus fermions, yeah. So you should study the phase structure. So if you have a certain pair of interactions, if you imagine like adding a term like, I don't know, minus psi bar psi squared, say with the right sign, then psi bar psi will condense, and then the phase of psi bar psi is this field. Yeah, that's right. Yeah, I didn't write down any interaction.
thanks.
Yeah.
Okay,